Hello everyone, my name is Dominique Atkins, and the title of my presentation is Eradicating Returns Only Sounds Good in the CS World. The article that this presentation covers is ROP Pecker, a generic and practical approach for defending against ROP attacks. First, giving credit to all the authors, we have Chang, Zhao, Yu, Ding, and Dang. They all come from the School of Information Systems at Singapore Management University. Assisting in research is ECE Department in SciLab from Carnegie Mellon University. This was presented February 22nd at the NDSS Symposium 2014. At the bottom you can find links to the article itself as well as the PowerPoint that was presented with it. What is ROP? ROP happens when an attacker gains control of the call stack and alters the program control flow to then execute machine instruction sequences that are already present in the memory. How does ROP protect against this? ROP Pecker effectively and efficiently defends against all types of ROP attacks without requiring source code and customized compiler support and binary rewriting. We would discuss the system breakdown that helps with ROP Pecker and how this combats the attacks. We have the goals, and we will have more on this later in the slides to come. ROP Pecker is basically to design a system that detects and prevents ROP attacks at runtime. We want a more generic approach with this defense, so it helps protect against all types of attacks. The gadget chain can be constructed by ret-based gadgets or jump-based gadgets, or both of them. Transparency is provided because the tool should work for all legacy binary applications. It's very efficient because this tool does not incur high overhead performance. We observed that a distinguishing feature of an ROP attack is the execution flow of a victim application that consists of a sufficiently long sequence of gadgets chained together by branching instructions. The main method of ROP attacks are to reuse instructions. These instructions come from existing code space to perform malicious operations. There are two steps to launch an attack. The first step is to identify a set of useful instruction sequences called gadgets from the entire code segment, for example, the application code and the shared libraries. The second step is to link the selected gadgets into a gadget chain through a crafted payload. A gadget has two sections, the first being a code section, which is for computation operations such as assigning a value to a general CPU register, and it has a link section which aids in manipulating the control flow. The manipulation is achieved through the indirect branch instructions such as ret and indirect jump call instructions. Indirect branches are utilized more so than direct branches due to the fact that direct branches cannot link, and this is due to their destinations being fixed. The features of these gadgets are very helpful. First off, we have a small size, which usually consists of 2 to 5 instructions, which is why multiple gadgets are needed. Although gadgets with larger code sections can perform more, they have more issues. An example being, a gadget can change the stack pointer, which can disrupt the next gadget's execution. Therefore, a true ROP needs a plethora of small gadgets. The next feature being scattered distribution. Gadgets are distributed across the vast code space, meaning the important ones aren't guaranteed to exist. For a higher success rate, an attacker would need a substantial code base to be able to collect enough gadgets to carry out a dangerous operation. This correlates with the small gadget size. Seeing that a gadget can have at most 5 instructions, more room to capture these gadgets are necessary. With the system overview, we get to look at the two-phase workflow, which is one being the offline pre-processing and the runtime detection phase. The offline pre-processing has 3 procedures. Number 1, extraction. This pulls all instruction information like offsets, types, alignment, things like that, of the protected applications as well as the shared libraries that they depend on. These are all extracted. Next being identification. The processor must identify what could be gadgets from the application binary and libraries. Then we have the analysis. And this analyzes the impacts on the code stack and the CPU instruction pointers, such as pop and push instructions can change CPU stack pointer. These must be analyzed to differentiate between safe or malicious gadgets. All of this is saved in what is called Instruction and Gadget Database, an IG database. Once this assembly commences, if an instruction sequence ends with indirect branching, and this can be identified as ret, jump, or what we have called as EAX address. If an instruction sequence ends with any of these and not direct branching, then it's a potential gadget. This gets further analyzed to determine the impact it may have. All in all, the preprocessor is needed to analyze a short sequence of code as opposed to dismantling the entire application code. Before we discuss the detection phase, there are two events that trigger the logic for detection. And this is the sliding window. This is application code pages outside the window are set as non-executable by the ROP Packer kernel module. This is what we have right here as you see in the image above. Because of this, an attempt to execute an instruction outside the current window activates a page fault exception. Then ROP Packer checking logic is announced. If no sign of ROP, then the old window slides to a new code page. For instance, the sliding window in Figure 2 consists of page B and C, as you can see right here. When the execution flow reaches to the log function, which is we have here in line 2, when the start function is executed on line 5, then page A is added to the sliding window and page C is deleted. And you can figure that out here once we have the new window, which is in the more darker color. Then it slides over to page A and page C is now forgotten. Due to the spatial locality of applications, using the window remarkably reduces the number of times the ROP checks, which reduces the performance overhead. Increasing the window size is a double-edged sword, though. It reduces the overhead performance, but it also increases the possibility for the attacker to launch an ROP attack with gadgets inside a certain window. Now this brings us to risky system calls. And these system calls are risky because they can bypass the exception that is raised when operating outside of the sliding window. A fix for this is to modify system call table so the kernel activates the ROP check logic before it sends the system call request. If an ROP payload is detected, ROP Packer rejects the request and terminates execution. Otherwise, execution flow is transferred back to the system call handler. Note this, only risky system calls are intercepted and invoked by protected apps. In the 3 stages of implementation, they contain so much information that they have to be belabored in their own slide. Here we have a more detailed slide for the runtime detection that lets us know more about the 3 stages of implementation. The ROP Packer kernel module, which we saw in the previous slide, is the brains of the process. It implements all the logic. It filters out irrelevant events that do not get triggered. For page fault exceptions, ROP Packer distinguishes exceptions triggered by the sliding window due to page fault error codes relevant to the sliding window that indicated the execute instructions in a non-executable code page, where on the other hand, the normal execution of applications never trigger page faults with the same kind of error code. For system call invocation, the kernel module compares the process ID of the invoker against the IDs of the target applications to discover relevant system calls. Since several integer comparisons take place, condition filtering is efficient. This is the first stage of implementation. Moving on. The pass payload detection utilizes LBR. This records source and destination address. To identify a gadget chain, ROP Packer verifies two requirements in each LBR entry. Instruction present at the source address is an indirect branch. Destination address points to a target. Once an entry satisfies at least one requirement, ROP Packer ceases checking and output the length of the gadget chain. If the length is greater than the threshold, an ROP tag is reported and terminates the application. If all is well, it proceeds to the future payload with the length as input parameters. Discussing the challenges faced, LBR isn't specific to application or processes, so we're coerced to weed out the records that belong to the protected application, since the records can enlarge the false negative or false positive rates of the ROP Packer detection. Solution for this is to start with the most recent, then traverse the whole queue backwards until one shows a context switch. This can be detected by looking at its addresses. A context switch is shown when its source address is in the kernel space and destination address is located in user space. Other branches keep their addresses in the same location. Once a context switch is found, ROP Packer stops because older entries are likely to be phony records. In LBR, new records override old ones when no more room is left in the buffer. This is an issue because there is no implementation that can intervene on the override or provide a backup of older branches. Also, phony records may occupy several entries in the already limited LBR register, and this leads to the selected gadget chain not being long enough to confirm an ROP attack, which demands further information from future payload detection. Future payload detection predicts any incoming gadgets along the execution flow. Although there are two methods to handle both gadget types, we will only focus on return-based, as jump-based gadgets are more salient in JOP, which is jump-oriented programming. Since return-based gadgets destinations are placed on the stack of the application and position can be calculated using the gadget instructions, there are two pop instructions that moves the stack pointer 8 bytes towards the stack base, while return retrieves the integer and the stack as the next destination and increases the stack pointer by 4 bytes. Following stack operations, repositioning the stack pointer will obtain the destination of the next gadget. The ROP Packer pre-processes this costly analysis and calculation offline and stores the results in the IG database to be queried at runtime. Again, the ROP Packer kernel module is needed for this to retrieve the results efficiently. Here we have at the bottom basically an image that shows each step, each stage of implementation. So we go to the condition filtering. If it doesn't give us any problems, then we go over here and then we just continue the original execution flow. If we do sense some problems, then we go down to the next stage, and that is the pass payload detection. If there's no problem, then we go over to the future payload detection. If we see there's a problem, then we have it identified as an ROP attack. If not, then there's no ROP, and we continue to the next, basically the original execution flow. Here we have the system goals, and which we basically alluded to in the overview slide. The first system goal is we just want a generic approach. This meaning that we want to be able to protect against all types of ROP attacks. Transparency is provided to work for all legacy binary applications. The efficiency is that this ROP Packer does not incur high performance overhead. And here we have the solutions that match up with each system goal that we're trying to accomplish. So we realize the importance of ROP attacks, and we want to protect against all of those. So that's how we basically handle the generic approach that we want. Transparency is provided due with the timing of checking. Efficiency is solved by the sliding window technique, and this helps us look through small sections of code instead of having to break down the entire section of code. The defensive approach that ROP Packer takes is by analyzing all gadgets that are located in the target application, binary, and shared libraries via offline preprocessing. During runtime checkpoints, ROP Packer identifies the gadget chain and the past execution flow using the history of taken branches recorded in what I mentioned earlier, LBR registers. LBR stands for last branch record, by the way. And also inspects a future execution flow to detect any ROP gadget chain leveraging the information from online analysis and occasional instruction emulation. Sliding window. Here we visit this again because this is very important in checking against the code and seeing if there is an ROP attack that is identified or detected. This sets the most recent visited code regions of the protected application executable and leaves the application code outside of the window as non-executable. This takes advantage of the temporal and spatial locality of the application. Here's an image that basically relays and compares the differences between all the other ROP defenses and ROP Packer itself. As you can see here, there is something. The first method we have is drop, and this only protects against return-based ROP types. Now, it does not need source code, so that's a good thing. But when it comes to the binary writing, that is needed, and the runtime efficiency is not that good. Here next we have ROP Defender. This is basically the same as the method above, drop. It's only focused on return-based types. It does not need the source code, but it will need a binary rewrite, and the runtime efficiency is not good. Next we have ROP Guard. This is similar to up above, but it's a tad bit different. It's the same because it still focuses on return-based types only. It does not need the source code. It will have to do some binary rewriting, but it is efficient at runtime. We have returnless kernel. This only focuses on return-based again, but this requires the source code, and that's how it's different between the methods up above. But there is no need for binary writing, and it is runtime efficient. Now we switch over to the methods that focus on our first goal, which is the generic approach, because these types are focused. This method, which is CF locking, the first one we'll look at, is focused on all types of ROP. The source code is needed, but there is no binary writing needed, and it is efficient at runtime. We have G-free, which is essentially the exact same as CF locking in terms of the ROP types, the source code issues, binary writing, and the efficiency. Next we have ILR. This focuses on all types of ROP types. There is no need for the source code, but binary rewriting will need to be handled. The efficiency in runtime is perfect, good to go. We have binary stirring. Now this handles all ROP types as well, but it's generally the exact same as ILR, due to the fact that the only problem with this is that binary writing will need to happen. We have CCFIR as well, which is generally the exact same in terms of binary rewriting being the only thing that's needed. K-bouncer is the same as well. The only thing needed is the binary writing. But when we want to focus on solving for generic approaches, transparency, and efficiency, and also remember transparency having to do with binary rewriting. If we want to solve all of those methods, then we have to focus on, or more so choose, ROP Packer, because this handles everything. It handles the generic approach, because it takes on all ROP types. Source code is not needed. Binary rewriting, not needed as well, which handles our transparency. And the runtime efficiency, which comes from the sliding window, which is huge in this case, helps us solve all three goals that we set out to accomplish in terms of defending against ROP attacks and diminishing the danger that adversaries can cause on our stack. This is my presentation on ROP Packer and how it handles and faces ROP attacks. I hope you all enjoyed it.